Hey everybody, my name is James Wadhwani. This should be my last video that I do. We'll see. Um, this is on XFLR 5 to get you guys familiar, and I will be going through the entire process of making a plane here, right? So I'll be going through the entire thing. I'll be explaining things as I go. I will be using um, information that I have taught in the previous, I think it was 4 videos that I've already made about aircraft basics, forces of flight, aircraft sizing, and then aerodynamics, stability, and control. So the very important information there is the aerodynamics, stability, and control lecture. Go ahead and watch that if you have not, because I'll be referencing that stuff a lot, okay? And subsequently, that video references all the videos before that. So really go watch all of them. Um, would be great. And then come back here if you haven't already watched those, and then we can get going to the X Flyer. All right. And I should say I don't really care if you watch those at 2 times speed. Just get that information down somehow. Find out what you don't know, and then let's go ahead and get started here. So when you go ahead and open X Flyer, a lot of people get confused, and I was confused too the first time I did this because you just get a blank screen here. Okay. Um, yeah, I have a dark mode on X Flyer, so I have some, kind of black bars and stuff like that. Yours might be white, so just make sure that's not too confusing for you. So anyway, up here is your module button. Okay, this is where you're going to be doing all of your important things for getting a plane or an airfoil analyzed. So the first thing we're going to go ahead and do is click on Direct Foil Design. Okay, that'll bring you to this screen. It starts off with a spline foil, and by the way, if you want to be able to see stuff better, you can go to Style here, click on this line, go to Width, and increase it. Okay, and then you can show foils here, right? You can show center lines. Um, so it starts with a spline foil. Don't worry about this. I usually just turn it off. Go up here to foil in the top left, and go ahead and hit NACA foils. Okay, so this is where you can put in a 4-digit or a 5-digit airfoil. Usually, in part, we use 4 or 5-digit NACA airfoils, so keep that in mind. But otherwise, you can. Um, well, there should be a way you can import a foil. You can export a foil actually. Do 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 do. Anyway, yeah, you can kind of make your own spline for a foil. Okay. So let's go ahead and get started with a foil here. So I'm going to go ahead and use what I know from Dodo, from the plane we previously built, um, as a way to kind of teach you guys. So it uses a NACA 6415. So go ahead and type in 6415 here. And I've always been told to do 200 panels for the amount of panels here. And you'll see that I'll refine the dots we have here to have a lot more dots. Okay, see that? You can name it whatever you want. I just keep it as NACA 6415 so it's not confusing. Okay. So you can show it here. If you turn on the center line, let me go ahead and up this color here. Change this color so it's different from our spline one, and then I'll increase the width so we can actually see it. You can see this is your mean camber line, right? I talked about that in the first video on the basics. So you can kind of see that there, right? Now here, I'll get into this later. You can also define flap settings, right? You can see trailing edge flap right here. You can see trailing edge X hinge, trailing edge Y hinge, right? And you can also see, right, I talked about 6% camber at 40% chord, right? 6415, right? So you can kind of see the things I was talking about back in that basics video about the thickness, the camber, and all that, right? And how that kind of translates here. Okay? So what you can actually do here as well is you can set flaps. Okay, so if you right click on your foil, there's a lot of options here. You can set your own camber and thickness too, so you can kind of customize airfoils. And you can also go ahead and set your flap. So this, right, it says flap, but this is really used for everything, for elevators, for ailerons, for flaps, anything that you want to deflect, right? You can do a leading edge flap, otherwise known as a slat, right? So you can see how that alters the front, the leading edge of the airfoil right there. But we're not going to go ahead and do that. We're going to do a trailing edge flap just so we can see it. Now, if we do negative 15 to deflect this thing up, right, because negative is up, we can change how far along the chord it starts at. Generally, with these kind of control surfaces, you do about a third of the chord. But again, I've talked about this earlier in my aero and stability and control lecture. You can figure out how big you want your elevator to be from XFLR and come back and change it. Okay. Now, if you're wondering, yes, you do have to make a separate airfoil for every single deflection, and you can see if you want to do something stupid like 20% of chord, but you really should never do that. If you want to change, we'll go 100% thickness here, right, to make sure it's the whole airfoil. Sorry, as I was saying, if you want to change various deflections, right? So you want to try negative 15, you want to try negative 10, which I recommend you do, especially with the elevator, all the way up to 20 or 25, not 50. That's not good. Then you're going to have to make a bunch of different foils, right? So this would be our NACA 6415 dash, I'm going to call it N15 for negative 15. Okay. So now we have a separate foil, which I'll go ahead and color. We'll go red. Okay. Make that a little bit bigger. And this is our deflected foil at negative 15 on the trailing edge flap. Okay. So I'm going to go ahead and actually make a new one as well and set that to positive 15. Okay. Just for later on in the video. Okay. Now, I recommend that you guys follow along with this video and do it with me, because that's honestly the best way that you're going to learn this, okay? You can watch this video, but I can almost guarantee you're going to forget everything if you don't do it by hand, okay? So right now, go ahead and pause the video and make yourself a NACA 6415, just as I did it here, okay? Make yourself a NACA 6415 with your negative deflection, which is up, and then make yourself one with the positive deflection, okay? Just like this, okay? Trailing edge flap, let's do 15 degrees, negative and positive, 70% of your chord, so, you know, about 2/3 the way along your chord at 100% thickness, okay? Go ahead and do that. So, once you've done that, let's go ahead and move on. All right, so we have our foils chosen here. Now you can go to XFoil Direct Analysis, okay? This is this screen. On the top left here, you have two options for plots, okay? This one right here shows your chord-wise distribution. Okay, so you can look at your velocity, your coefficient of pressure, and if you remember back to, I think it was the Forces of Flight video, we looked at a CP plot, and I'll go ahead and show you that again once we get this going. So if you wanted to do an airfoil analysis and just look at the airfoil, what you would do is you would select your airfoil on the left here, okay? Kind of where I'm clicking around. So we're going to go ahead and look at the 6415. Then we're going to come up here to Analysis, okay? And we're going to click Define an Analysis, all right? So here you can choose your name. I just let it go automatic. You have different types of analysis here, okay? So this depends what parameters you can put into it, all right? I like to do a type 1, and this way we need to figure out a Reynolds number we're going to be looking at, okay? So by this point, when you're doing airfoil selection, you should have a chord length and a cruise speed and a loiter speed in mind, okay? Now, when you're choosing your airfoil, you'd probably want to size it for your cruise speed, but if you're doing a plane that needs to loiter a lot, maybe you want to do that for your loiter speed too. All right, so Reynolds number, I went over this in the basics video. You guys should definitely know what this is, but we're going to go ahead and figure out what our Reynolds number is for our airfoil. Now, I said I was going to base this off of Dodo. Dodo had a 14-inch chord. Okay, so that's our characteristic length, our chord, if you remember that equation. Let me go ahead and pull that up. Okay. Just go to images here, find the first one we can. Here we go. So we're going to use this kind of middle equation right here. Whoa, hello. Okay, so it's rho v d. D here is in place of our length, right? I remember I said this could be used for pipes as well, so we'd have L or C for a chord length, right, over mu. So mu is this is our dynamic viscosity, rho is our air density, v is our velocity, and then d in this case, which I would write as L, is our characteristic length, right? So characteristic length, 14 inches. Dodo was chosen to cruise at 19 meters per second, so that would be our v, would be 19 meters per second. Yes, I am mixing units. Yes, it is terrible. Yes, that is how I operate. So rho in this case is 1.225. That's kind of the standard number, kilograms per meters cubed. Okay. Now mu, right? What is this dynamic viscosity? Well, I like to use this thing called the engineering toolbox. Okay. Um, this is a wonderful website. So we can go down here and choose our temperature. Let's use 20 degrees C because that's pretty standard, and calculate our dynamic viscosity. So we get 18.13 Pascal seconds. Okay. Now this is a very easy equation. This is literally 4 variables, but I am going to go ahead and use a calculator because I don't want to type this into a computer, and I'd rather be able to type in inches, right? So it's 14 inches for our chord length. Whoever Dominic is, thank you for doing this, buddy. Fluid velocity is 19 meters per second, okay? And then our fluid density is 1.225 kilogram per meters cubed, as I said before. And our dynamic viscosity here was that, what was it, 18.13 Pascal seconds, okay? E negative 6, all right? So this gives us a Reynolds number of 456,514. So let's go ahead and copy that, come back here to our analysis, and throw that in, okay? So as you're following along, get these values just like I did, okay? Now the Mach number here, you guys know Mach number, that is, I haven't explained that one yet, that is your velocity with respect to speed of sound, right? So if we go ahead and look up, speed of sound at sea level, okay, that's going to be 343 meters per second. All right. Now we're flying at 19, so the Mach number is equal to our speed divided by, not 91. You can see I'm looking up Corvettes. Anyway, 19 meters per second divided by 343. Right. So our Mach number is 0.055. All right. So let's go ahead and throw that in. There you go. Okay. So we have our Reynolds number 456,514. And our Mach number, 0.055. Okay. Now N-crit, what is N-crit? So the N-crit number is a number that essentially determines the sensitivity of the flow to disturbances, right, that contribute to be turbulent. Okay. So we usually leave this at 9, right? So here in this box, we're deciding settings for our transition. All right, this is our transition from laminar to turbulent flow. Again, N-crit at 9 is a good value to use. If you want to force the transition of the flow at a certain point, you can use triplication. Okay, this is in basically percent divided by 100, right? So 0.5 would be 50%. 1 is 100%, right? And if you think about that, that means that we're at 100% of the chord. So we're forcing it to trip after the chord. So we're not forcing it to trip on our wing. All right. So go ahead and leave this at 9, 1, and 1 for our purposes. Okay. So you can see in the left here under our 6415, we now have an analysis described. All right. So here, what we're going to go ahead and do is on the right side, we have our analysis settings. All right. We are going to use an alpha, right, angle of attack change, and we're going to sequence it. So click that sequence box. Now, change your start to 0 and your end to 20, and your delta, which is your difference between points, do 0.25. Okay. Click on init.bl and store op here. And then go ahead and press analyze. Okay. Now it's going to come up with all of these converge points. It says some points are unconverged. That is normal. So go ahead and hit close. XFLR, I'm going to say this a lot this video, XFLR kind of sucks. If you click on a plot and then you press R, it will automatically resize it, okay? So just R, no control, just R. It'll resize it, okay? And this gives you a plot of whatever you want, right? So here I have 5 graphs pulled up. You can click up here and you can click on individual graphs, or you can set 2 graphs or 4 graphs or all graphs, okay? I'm going to keep all of them. If you double click on a plot, you can change your values, right? So we can look at CL versus alpha. We could even look at alpha versus alpha, which is, as you might imagine, 1 to 1. We can look at CD versus alpha. We can look at CD times 10,000, which is, I believe this is so you can see drag counts, which is kind of a unit of CD. Coefficient of moment, if you want to, right? You can see that transition location, okay? And your CL over CD, okay? So the important ones for analyzing airfoil are going to be, most importantly, CL alpha, and then CD alpha, and then CL over CD alpha. Okay, so I'm going to go to 4 graphs here. So we're going to be looking at top left, top right, and bottom right. Now, in your sequence box, go from 0 to -10. Okay. Same delta, and analyze it. Now, you might be asking, why didn't we just go from -10 to 20? Well, the reason for that is XFLR is, for some reason, very bad at going from negative to positive numbers in one sweep. I don't know why, but that is something I've been told by professors and other people I know who have used XFLR. So make sure that you're going from 0 to your positive and then from 0 to your negative every single time. Okay. I believe it's something about starting at low alphas and then going higher. Okay. But anyway, just the important thing here is to make sure that you do that. Now you can scroll along your line here by clicking. I'm clicking and dragging here to get to different values. So what you can also do here is right-click on your point, right, your data set, and hit Edit Data Points. And here you can see all of your points and the numbers associated. So if we're looking at we know for our wing we need a CL of 0.6, for example, at 3 degrees alpha. Okay, we go to 3 degrees alpha, and our CL is actually very high, 0.999, that's great, right? So that's something you can do. You can also right-click here, and you can hit on Export. Okay, and that would export it to a comma-separated value file. Okay. Now, moving on, we're going to go ahead and show you batch analysis. All right. Now, the batch analysis is for when you want to look at a 3D airfoil. Okay. Also, if you're analyzing a lot of airfoils, you can use this for that as well. So right now, go ahead and go back to direct foil design. And since we're going to be looking at an actual plane, we need to define all of the airfoils that we're using for that aircraft. Now, we're not going to use the same airfoil that we use for our main wing for our tail, right? We're going to probably want to use a symmetric airfoil for our tail. So go ahead and go to Foil, go to NACA Foils, and let's do a 0012, okay? 0% camber, 12% thickness, all right? Name it 0012. We're not going to do any flap deflections. We're going to keep that for the main wing, okay? But just keep in mind as you go through this, it's the same idea. And you can see that guy right here. Right, the camber line is equal to the chord line. Now go ahead and go to our direct analysis again. You see that airfoil is now popped up. So go to analysis and press batch analysis this time. Now this screen can look a little bit confusing. The first thing I want you guys to do is select every single airfoil that we have here. Make sure they're all highlighted. Okay, so mine are all highlighted here. And then I'm just going to go ahead and delete everything. No, there's no easier way to do this that I know of. If you find out an easier way, I don't care if this is 5 years down the line, find me somehow and tell me, because this is the most annoying thing ever. But go through and delete every single thing, all right? So pause the video here, delete every single Reynolds number in here, and then come back once you're done. Okay. So now you should have deleted every single one but one, because it won't let you delete the last one. Now, how XFLR works is it takes 2D data, okay, from the 2D airfoil that we're looking at now, and it interpolates. It does not actually extrapolate. I did some research. It does not extrapolate. It only interpolates all of that data to get 3D solutions. So you need to give it a lot of data, because if it ever hits a point that is outside of your 2D data, it will not know what to do, and it will not give you results. So, that being said, you guys remember what we did last time, right? We tried to find the Reynolds number for our main wing, right? And that was off that 14-inch cord. Well, what's different this time? What's different is we now have the tail airfoil. And our tail, for Dodo at least, did not have a 14-inch cord. Your cord is very likely going to be different. So I'm going to go ahead and, first off, make note of the last one we used, which I think was... it was 456,000 or something. Let me go ahead and check that. I think I have that pulled up here. Yes, 465,000. Okay. So I'm going to go ahead and copy that over here. And I don't know what this is. Apparently this is 456,000. Is that Polish or something? Anyway, sorry. Go ahead and change your characteristic linear dimension, which is our chord length, to that of the tail. Now for Dodo, that was 9 inches. So if we go ahead and enter that here, you'll see our tail Reynolds number is 293,473. So I'm going to throw that in as well, and you can see this is something different. It's funny that this random stuff comes up. There's like a model train. Okay. Anyway, so I'll move this to my second screen so I keep that up. Yes, I am cool like that. So let's go ahead and start at a low Reynolds number, just so that we hit those points, those far extremity points, so that it does not is able to interpolate if we have any points there. So we're going to start at a low Reynolds number, which is a high normal number, but it's a low Reynolds number, is 100,000. Okay, so 100, 1, 2, 3, 100,000. And remember, our Mach number here is 0.055, so let's go ahead and throw that in. Keep your end crit at 9, and then hit insert after. Now we're going to have 100,000 space and go to 200,000. Now, the more points that you give XFLR, the better it is going to be at interpolating, right? Because it's able to create closer sort of linear relations, right, that are closer to the actual value with more data. So I hope you can kind of see how that might work. Okay. So, right, our tail Reynolds number was 293,473. We want to make a cloud of points around our Reynolds numbers that we're going to be looking at. So one of those is for our tail, 293,000, and one of them is for our main wing, 456,000. So now I'm going to be going to 225,000. Okay? And then I'm going to go 250,000. So follow along with me here, 250,000. And then I'm going to go 275,000. And then let's go to 280,000. And then let's go to 290,000. And then 300,000. Okay, so we are getting closer and closer points around that 293,000. I'm not hitting the 293. You can hit the 293 if you want. Let's actually go ahead and do that just for the sake of this. So let's go 293,473 is what we were looking at. Okay, 300,000. And then let's go ahead and do 310,000. And then get the points farther and farther away, okay? So then go ahead and do 325,000. And then let's go 350,000. And then let's go 400,000. This is really annoying. I wish that there was a way. Again, I've always said this. If you're ever going to do a startup or you want to make your own software, redo XFLR to make it more user-friendly. It's already very user-friendly, but if there was a way I could just put in the two Reynolds numbers I want to look at and it makes all these like cloud Reynolds numbers for me, that'd be incredible. Okay, ignore Mountain playing Counter-Strike 2. I have this thing on Do Not Disturb. I don't know why it's doing that. Let's kill Steam. Okay, 400,000. All right. Now we're getting kind of, well, actually, I was going to say we're getting farther away. Now we're hitting the range of our 456,000. So let's go ahead and do 425,000, right? Okay. And then let's do 400 and, well, we're looking at 456. Let's do 440,000. Okay. And then let's do 450,000. And then let's do our 456,000, 514. And then let's do 465,000. Okay, right? Just points that are close to it. And then we'll go to 475,000. And then to 500,000, okay? Now I'm going to go by 100,000, again, to get those extreme points. So 600,000. And then 700,000. And then let's go 800,000. Now we're getting pretty far away. Okay, let's go ahead and do 1,000,000. So 1e6. Okay, and then just for the heck of it, let's do 1.2e6. I'm probably not going to hit that, but let's just get it. So now we have a vast number of... I don't know why my Mach numbers changed to... I don't know. That's fine. I don't know why I did that. Anyway, we have a vast number of Reynolds numbers. Okay. Again, keep that top and bottom transition location to 1 and 1. Now here you'll notice we have the alpha thing again, and you'll notice I'm going from -10 to 25 with an increment of 1. Let's change this to 0.5 and let's just go up to 20. We don't need 25 here. But right, I'm going negative to positive. That's illegal. Well, notice now we have the from 0 button. Why this isn't in the normal analysis, I don't know. Again, somebody please make your own XFLR. Change your threads to something under your max amount. I'm going to do 10. I like to go 2 under. This just helps, I believe this is for using your CPU a little bit better. And helps you get this done faster. Then go ahead and hit Analyze, okay? Just going to go through all of them. Some of them take longer than others. All right. So, yeah, go ahead and make sure you're caught up now and get this analysis done. Okay, so I went ahead and clipped that, um, so you didn't have to sit there and watch. It didn't take that long, maybe a minute, but it got all these done. Okay, and analysis completed. Look out for that. Now hit close. All right. Now you'll notice, right? Oh my God, what the heck is going on? This is all of your Reynolds numbers. Okay. Um, Most of them follow the same line. Okay. You have some outliers, probably at the very, very low Reynolds numbers or the very, very high Reynolds numbers. Um, but yeah, right? Pretty crazy. So, and I'm going to go ahead and you can right click here and you can, well, you can also left click and you can decrease the thickness. I'm going to do that because this is a pain to look at. All right, there you go. And I'm actually going to turn off the symbols too. We don't need those. Okay, right. So that's what that looks like. Pretty cool. Pretty cool looking, right? So again, you can hit R on these. And then I'm going to go over here too. And this is, oh boy. Hopefully my computer doesn't crash. This is your CP plot. Maybe don't go over here if your computer's slow. Um, and you can kind of, well, you can click the X here to turn off certain ones. Okay. If you click on this, it'll turn on all of them. Okay. But you can also click on individual ones for certain certain alphas. Okay, so let's go ahead and look at something interesting. Let's look at our symmetric one. Okay, now if you remember in the CP plot, it kind of tells you how much lift you're getting in a way. Let's go to our 293. That's where we're going to have this tail. And let's look at 5 degrees alpha. Okay, let's turn this guy on. Now you can actually see the airfoil here in the alpha it's at. Now, if you remember the CP plot, right, this is our top surface, right, because the y-axis is flipped, and you can see our negative CP up there, right? So lower CP on the top surface and higher on the bottom. Now, remember, this is a symmetric airfoil, so we should be getting no lift at 0 degrees alpha. So let's go ahead and see, right? Well, okay, maybe you're getting some lift. But either way, you can see. Oh, I haven't even selected it. That's why. There you go. 0 degrees alpha. Okay. So you can see now the CP lines are directly on top of each other. Okay. There's only one line, which means you are getting no lift. Okay. And then again, we go to 2 degrees. We go to 0.5 degrees. You can see that the line's kind of slowly getting farther and farther away from each other. So there's 0, there's 0.5, and there's 2 degrees. Okay. So anyway, I digress. I just wanted to show you that. Pretty cool. So you can kind of see, and that was along the chord. You can see the chord wise distribution of this. So let's go ahead and turn these guys back on so we can see them again. Now we have our batch analysis done. Okay, this is big. This is a big moment for us. So go ahead and pat yourself on the back. I don't know why you did that, but anyway. Now we're going to go to our wing and plane design. So back up to module and hit wing and plane design. Okay. Now up here we have a lot more options. Okay, and I'll go through each of these. First and foremost is our 3D view. I love the 3D view. Very cool. Hit Control click to zoom around, look around, scroll in, scroll out. If I can remember how to scroll in and out, actually. I think this is scrolling in and out with the scroll wheel. And then go ahead and go to plane. Okay, hit define a new plane. All right, and this popped up off my screen, but here it is. Now you'll see this plane is kind of flat and grayed out. That's because we don't have any airfoils selected yet for it. So you can make a biplane if you want, and you can change your Z position, which is your vertical position of the other wing. So if we go 5 inches. And actually, real quick while I'm here, okay, pause this video. Well, not right now. Pause it in a second. Go to your options, preferences at the top. Go to units and change your length to inches. Okay. Yes, I mix imperial and metric units. Yes, it's terrible. Yes, I love it. Okay. Just your length, nothing else. Okay. Keep meters squared and everything because this is important for our wing loading. We like to see our area, and our speed's always calculated in meters per second. And mass, I've started thinking kilograms, so I'm keeping it at that. But you could do pounds for that, I suppose. Okay. Go back to plane. Define a new plane. Okay. Here we're going to define our main wing. Right. So this is kind of buggy, right? Again, if you did anything in life, make a new XFLR. These should be showing up. They don't, but when you click on them, they do. So for foil, go ahead and select our 6415. Okay. So this is what it looks like now. Now down here, you can change your view. You can also just scroll around on your own. But we're going to go in a top-down view here. Now notice our wing here has some taper. right? The leading edge is swept. Remember, I hate swept leading edge wings for RC planes, so we're going to demolish that, right? So you have two rows here. If anybody can tell me why, you've probably used XFLR before, or you're very intuitive. But the first line is for our root position, okay? Now this is mirrored, right? So if I want there to be a 5-inch gap, maybe for the fuselage in the middle, then I do a 2.5 inch here, and it does 2.5 either side. So from the x-axis to the wing is 2.5 inches here, but the total distance is 5 inches, okay? So we're going to keep this at 0, but this is to prove to you that, like, this is for the root, okay? And this is for the tip, okay? So now Dodo had a 14-inch cord, and it was a rectangular wing, so it's 14-inch on the root and on the tip, okay? Just like that. Now we have some offset here. We have some sweep. We don't like that. We want 0, so change your offset on the tip to 0. Just like that. Now it's a nice rectangular wing. And Dodo had a 120-inch, a 10-foot wingspan. So we're going to do half of that, right? Because it's mirrored. So we're going to go ahead and do 60 inches for our Y, for our tip. Okay, there we go. So this is kind of what Dodo's wing looked like. All right. You can see it from the side. There's our airfoil. And you can also add, if you have a more complex wing geometry, you can add more points. And I'll get into this later, but you can insert after section 1, and let's say I did an offset here of 10 inches, right? That midpoint is now offset by 10. Now, if I were to offset the tip by 10, it does not add on to that 10 inches. It goes back to being flat with the 10. So if I wanted a continuously swept wing, I'd have to go to 20. Now, you can do aerodynamic twists here, and I brought up aerodynamic twist I think in the Forces of Flight video, and you can change your foil on the tip. So we could do a 12, right? So now we have a symmetric airfoil on our wing tip and a cambered one on the inside, which is pretty cool, right? We're not going to do that. Dodo did not have aerodynamic twist. You could also change the geometric twist, so we could do negative 10 degrees here to make the wing tips angled down. Pretty cool, right? But again, Dodo was a very simple wing. Did not have that. Did not have anything crazy. Just had, if we go to 60 here, just had a rectangular wing. Okay. Now X panels and Y panels. Okay. These you can see if you click on the panels button here on the right, and this is, I mean, it just shows what panels are on the wing. So XFLR uses 3D panel method and vortex lattice method. Okay, these are two different 3D methods. These are what uses that 2D airfoil data, interpolates it, and then expands it into a wing. It does that through, as you can imagine, panels. So what I usually do is I make sure that the panels look good. So you can see here our panels are quite wide. So we may want to increase the number of Y panels. Let's go to maybe 15 here for the tip and the root. Okay, just to add a few more in there. You can also change the distribution, right? So a cosine will kind of bunch it up at the leading edge and trailing edge and at the tips, which you can kind of see here, right? These panels are a lot more bunched up here in the corner. We can change that to a uniform distribution to make them all uniform. I'm going to keep in cosine here, and I'm going to go ahead and do 15 panels here. Let's go 20 in the Y, actually. And let's do 20 here, and then 15 here. Again, these numbers are disappearing. Kind of annoying. So there we go, right? Looks good. So go ahead and hit save. All right, so this is our wing. Now you can see our tail's looking a bit small there. If you guys remember in my aero and S&C lecture, I talked about the tail volume coefficient. So that determines how far back it is, and how big the tail is, right? That'll be X position here. So for Dodo, I think it was like 57 inches or something like that. So now our what they call the elevator, but really is the horizontal stabilizer, is way back here. For the fin, or the vertical stabilizer, don't call it a fin. It sounds like this guy's never seen a plane before. This is a vertical stabilizer. Move that back to 57 too, to put them right on top of each other. Now we're gonna, if you hit define on the elevator, we're gonna change our full to the NACA 0012. Now this one, like I said before, had a 9-inch cord. Okay. And no sweep, 0 sweep. I hate sweep. And then, as you can see, our panels are quite stretched vertically. So in the X direction, we might up this to 14. Okay. And let's go ahead and increase our span here to, ooh, I don't know. Maybe it was around 20 inches. Does that look good? I think that looks about right. Let's do 24 inches, so 12 inches each side to make it look a little better. And I go and hit save, right? So there's our tail back there, maybe a little bit big, but we can change that later. And I'll show you exactly how you should know if you should change that. But again, if you got your tail volume coefficient correct, then you should be fine, right? So now our fin, we're going to do the same thing. Going to use that same 0012 airfoil, okay? And again, 0 offset here. This one also had a 9-inch cord, and I think this one was, I don't know, let's do 12 inches tall. Okay, all right, so there we have it. Again, those panels are a little big, so I'm gonna, let's go 10 here, all right? That's a good amount, 13.5. All right, let's do 10 here, 10 here, okay, all right. So there we go, okay. Looking pretty good. So hit save, right? So here is our plane. And one more thing before we continue here, right? Dodo was a high wing plane. So the tail was actually a little bit lower than the main wing. So we're going to go ahead and bring the Z down by, let's say, -10 inches, which I don't know if that's accurate, but I'm going to just kind of make that up, right? So now you can see it's kind of a high wing. Now you might be saying, okay, we've got the wings in. What about the fuselage? What about the body? You can see here there's a warning. Including the body in the analysis is not recommended. XFLR does not do analysis of a fuselage very well. So we're just going to, the convention is just keeping the wing and the tail in there and not doing anything else. I should note here you can change the tilt angle of the elevator and of the wing. Okay, this is called the angle of incidence. We're going to keep the tilt angle of the tail at 0 for now because we're going to go through a stability process to show you guys how you should determine this tilt angle. If you remember back to the Aero and SSC lecture, right, this tilt angle is important for our longitudinal static stability, okay? So if we go ahead and look at, oh, I'm in the wrong section here, first off. If we look at this guy, right, the effect of your elevator position, so elevator down, elevator up, changes where your x-intercept, where your CM0 is, right? And this is the same thing, right? This is elevator position, but it works in the same way as changing that angle of incidence for the tail. Okay. So let's keep that at 0 for now. All right, the tilt angle, I'm going to go ahead and use Dodo's, was 1.5 degrees for the main wing. Okay, because we cruise along at a certain alpha. This does change a little bit the neutral point of your plane, so I like to keep it a little bit low. But the idea is, right, you want to be cruising along with a low tilt angle on your wing. Okay, so go ahead and save that. Now here we have our plane, right? Pretty cool. So we're going to do the same, if I can master zooming in here, we're going to go ahead and do the same thing that we did with our airfoil, which is define an analysis, okay? So go ahead and hit define an analysis up here. And now we have a couple different types. This is type 1 fixed speed. This is what we're going to use to start, okay? Dodo used 19 meters per second as its cruise speed, so we're going to go ahead and enter that. And that's also what we defined our Reynolds numbers for. If you had a loiter speed, you should go back to the batch analysis and change more Reynolds numbers for that loiter speed as well, so you can test that. Beta, again, is our side slip angle. We're not going to do anything with that just now. So you'll notice how now we have our analysis method. I'm going to go ahead and do ring vortex, VLM2. Okay. We want viscous on. So XFLR doesn't really account for viscous effects. It is non-viscous, so kind of no air friction that deforms the flow, right? And it adds kind of viscous effects taken off of 2D geometry to make more of a realistic outcome at the end of it. So we're going to keep that on. Inertia, we're going to use the plane inertia, but we haven't defined any yet, so we'll go back and do that. Reference dimensions, I always use plan form projected on the XY plane. Aero data, keep in these default values. These are pretty good. And extra drag, right? Okay, looks good. So we're going to go ahead and hit save. So here we have another sequence. So click that on, and remember, negative to positive is not very good. Go 0 to 20, and let's go by 0.5 this time on the delta, and hit analyze. Okay, and then go 0 to -10. Now you'll notice we did actually make it all the way to -10. We only made it to 12 on our positive. alphas, right? Again, this is because XFLR sucks. so, so it only made it up to 12. Remember where our airfoil stalls, right? It's around 13 to 15 degrees. So when we get to the stall region, it kind of breaks down. So if you look at the plots here, if we look at our CL versus alpha, so I'm gonna change this to CL versus alpha. We never, it's perfectly linear, right? We never even get to the stall region where it becomes nonlinear. So, right, we are looking at the perfectly non-stalled flight envelope for this plane, okay, which is okay. We can work with that. So now what I like showing people is you can see your coefficient of pressure here and how that's distributed. You can look at lift, see your lift vector, and you can see how that changes along the wing, how it gets bigger at higher alphas, and how it actually gets negative at lower alphas. You can see at some points it starts to freak out. Okay, this is probably because we either have a bad amount of panels, or our Reynolds number is does not have enough points. Okay, for a realistic evaluation. This is okay for us, but if you see this in your analysis and you're actually trying to get some stuff done, go ahead and see if you can add more Reynolds numbers, and also do some research and see how you can kind of fix this. So my favorite though is looking at the downwash, right? Because we can see, sorry, not downwash, the stream, because we can see the wingtip vertices, right? And if you go ahead and hit surfaces, you can click those back on, and you can see, right, how those kind of spiral off the wings. So this should show you how that kind of higher aspect ratio is good, right? Because the smaller our wing is, right, the more that sort of affects the inboard side of our main wing. And our tail's looking good there too, right? You can also animate this. I like animating this. Turn up the speed. You can see how it kind of forms, right? Pretty cool. Going through the different alphas. Anyway, pretty cool. So let's go ahead and turn off stream here. And we're going to go ahead and define a mass. All right. So right now our CM alpha plot, CM alpha, looks like this, right? We don't even have a static margin because there is no mass. So to be honest, I'm not too sure how they're even getting a stability profile line. Maybe there's like a default mass that it puts in. But that's the wrong button. If you right click on the plane name, you can press edit. Okay. Then go ahead and press plane inertia. All right. It should bring up this little, very large tab here. Okay. I'm gonna make this smaller if I can. There we go. Okay. So right now we're at 0 kg. Dodo was about 19.2 kilograms. I'm gonna do 19 here, and we're gonna start this off at quarter chord. Now, if you look at our axes here, you probably can't see it, but the y-axis, the x-axis begins on the leading edge of the wing. So if we want to start this at half chord, which is quarter to half chord, is probably a good starting point. We're going to go ahead and do 7 inches, okay? And we're going to go ahead and hit save. Now, I will show you this later. For a static stability analysis, it does not do rates, and so it does not do inertias, right? Inertia depends on where your point masses are spread out throughout the plane. Static analysis does not care about that. It only cares about your center of gravity location. So by only defining a center of gravity, you're able to alter that center of gravity much easier, and you are able to move it around to define your stability analysis, your static stability analysis. Later on, when we do the dynamic stability analysis, I will show you that you need those points in, those point masses for every single component. And the more components you have, the more realistic your dynamic analysis is going to be. There is no way to import a CSV file into here that I know of. Again, even if it's 2050 by the time you're watching this and you figure this out, find me somehow and let me know. Because we had to have some people go through and put in. I did not do this myself, but we had to have people go through and put in all those masses, and it sucked. So, right, keep that in mind. Okay, and that's how you get your inertia, right? Right now we have 0 inertia because we have 0 point masses around our CG. We only have the CG. Anyway, so now if you were to hit masses here, you can see our CG is right here, right? And that is just about, well, it should be exactly half chord, right? 7 inches of a, that's not what I meant to do. 7 inches through a 14-inch wing. So yeah, you can kind of see it there. If you zoom out, it becomes bigger. Kind of goes into the wing at some point. I am also going to move that down actually, right? Because this is a high wing. Let's go -5 in the Y. Sorry, not Y. Z. -5 there. Just to move it down, right? Because this would be where our fuselage would be. So go ahead and hit save. But really, it only matters on the x-axis. So it's going to say it'll erase all the results associated with this plane. This is okay. We'll just rerun this analysis to 0 to 20 and then 0 to -10. This will happen a lot as you're trying to determine your stability profile, which is okay. We can survive. So now that we have that mass in, let's go ahead and go to this second from the left plot here to see what that looks like. So now our CM alpha, this is interesting. Our CM alpha is fascinating. It's curved and it's basically neutrally stable at 0 alpha. We do become stable over here, but as we go into negative alphas, we're unstable, which is really interesting. So what this tells us, right, if you remember our plot here from our stability lecture of our CG location, we want this to be more stable because we're currently neutrally stable. So what we can do is we can move our CG forward to make it more stable, okay, to make this line more negative. So we're going to try that. We're going to see what happens. And just so I can compare here, we'll do this as well so we're all on the same page. But when you're actually doing this, don't make a new plane. But I'm going to go ahead and duplicate this, and we're going to call this plane name 2, whatever you want. And we're going to go ahead and edit this, go to our plane inertia, and we're going to move this forward from half chord. So we're going to go, let's try 4 inches. Let's be a bit more extreme. Okay. So now if we go back to our plane, right, this little plane icon here, and we turn on our masses for this guy, we can see it's much farther forward than our first plane. Okay. Now we're going to define analysis again at our 19 meters per second, and we're going to run that 0 to 20 and 0 to -10. Okay. And by the way, have init, LLT, and store op point selected here. If you didn't have that selected before, that's fine, but you should have that selected. So now we can see, right? So let's go ahead and change this color. It's cool seeing me be correct. I love being correct about things. We're going to do red for our first one because red is bad, and blue for our second one. Now we have a much more stable plane, right? You can see it's no longer neutrally stable at 0. It is a fully stable profile from the alphas that we get out of it, okay? And you can kind of see how that works. Now what I'm going to do is point out a couple things. First off, you guys remember trim alpha from our slides here, right? It's the point at which we cross the x-axis when we have no coefficient of moment. That is negative. So what does this tell us? This tells us that when we're cruising along at this speed with this current plane configuration, we're going to be at a negative alpha. Is that what we want? No, that's not what we want at all, because that means we are going down, right? So right now, I'm going to ask you to pull up 2 plots. The first one is a CM alpha plot, which you should have up if you're looking at this at this point. The second one is make this an FZ here, so you have to scroll down a bit, find FZ versus alpha plot, okay? And that'll look like a straight line like this. Now for our plane name 2, we are going to go ahead and define a different kind of analysis. And this is going to be a type 2 fixed lift. Okay, so this is basically taking, and this will tell us our wing loading too, which is kind of cool. But this is basically taking the weight of your plane and making sure that you are putting out just as much lift as you weigh for the entire analysis. Okay, go from 0 to 20 on this and hit analyze. Okay, now you will see, I'm going to make this line green, dark green. Okay, let's make it a little bit bigger too. We have this line here. Effectively, I use this line to determine our point at which we make enough lift to fly. Okay, I hope that makes sense to you. So this is basically saying if we're making as much lift as we weigh, this is our weight. And that is 186.5-ish newtons. Okay? So this tells us that at current, we need to fly at just above 2 alpha in order to make enough lift for our plane to stay in the air. So what I like to do is kind of center around these plots, and I like to scroll through these points by clicking and dragging. Now, I like to get to the point at which either I cross the trim alpha, which in our case is about here, and you can see we are making about 60 newtons of lift, so our plane would not be flying in this case. Or I like to go to our FC point, and I can see that our coefficient of moment is pitching horrendously down at this point. So this is not what we want, right? Well, how can we fix this? Let's go back to our plots here. That's a lot of writing on that one. Remember, right, this is the effect of our elevator position. So the more that we move it up, the more it's going to move towards the higher alpha side or the higher CL side. So let's go ahead and try a more negative deflection. And right, remember I said earlier that Dodo did have a negative, or maybe I didn't say it, but Dodo did have a negative deflection. So I kind of saw this coming. Your plane is probably going to have a negative deflection on the tail. So go ahead and edit this one more time, and let's change our tilt angle to something a bit more extreme. Let's go -2 degrees, okay? And hit save. Again, it will erase all your points, so go ahead and run this from 0 to 20, and then to 0 to -10. And then do your fixed lift as well from 0 to 20. You don't need to go negative on this one for the point of this graph, but you can. So now let's look at our plots, okay? How are we doing? We're a little bit closer. So what's happening here is, let's go to our thing here. So now we're making over 100 newtons of lift at this point, but we're still trimming at a negative alpha. You never, ever, ever want to trim at a negative alpha. So let's go ahead and change this again to see what we can do. Now, what we can also do is we can make our plane less stable, right? We can make this slope less negative to have it intercept at a better point. Okay. So let's go ahead and try that as well. So let's go ahead and edit our plane once more, which we're going to be doing a lot of. Let's go ahead and define our inertia, and let's move that back a little bit. Let's try, well, since 7 was neutrally stable, 4 is a little bit too stable. Let's go ahead and try something like 4.5. Sorry, 5.5 is what I meant. 5.5 there. Okay, save that. And then go to your elevator angle and change this tilt angle even further. Let's go 3 degrees, okay? Now, you should not really be going to any sort of higher degree on your tail angle of incidence, okay? What this does is it adds more drag because your tail's always putting in some amount of lift. You should have a minimal amount of tail deflection as possible. But now this shows us that we're cruising at about 5 degrees alpha, pretty much on the dot. And once you're past the negative line, you don't necessarily have to go to negative alphas in your analysis because you can see everything here. But now this shows us that at 5 degrees, right? Oh my goodness! Now we are way past. We're climbing basically. We're producing more lift than we weigh. Okay. So now we want to kind of ease this back a bit. All right. Maybe our tail deflection was a little bit too much. So we want to translate this line to the left. So let's go back. Let's edit this once more, and let's try -2.5. Okay. See how that goes. And then I'm going to go ahead and analyze this. So now we're cruising at about 4 degrees alpha. That looks a little bit more promising. And our line here. So let's go to 4 alpha. Still a bit high, right? So making our plane less stable had quite the effect on our plane here. So let's try -1.5 degrees. All right, see how that goes. And you guys can also, if you're not getting enough performance out of your tail, right? You're not moving your line enough. You can make your plane bigger, or your tail bigger, or you can move it farther back, right? You can make your tail volume coefficient even larger, right? That's a way you can solve this too. So now, as we cross our line here, we're at about our trim alpha is about 2.1 degrees, and we make that much lift at about. Well, we make about that much lift at about 2.1 degrees. Okay, so we're pretty dang close here. That's a pretty dang good spot to be. Okay. Why is this line? Oh, there we go. Right, that's pretty good. Okay. So at this point, we're making just about as much lift as we need to fly, and we're just below our trim alpha. If you want to get this perfect, you can, but for the sake of this video, right, this is a good spot. All right, this is a vast oversimplification of the flight of your plane. This is assuming 0 elevator deflection. We're only changing the angle of the entire elevator, and it's assuming that you're flying at perfectly 19 meters per second. In real life, if you're not producing enough lift to fly at this point, your plane's going to nose down a little bit, and you're going to gain some speed, and then the amount of lift you're creating is going to go right back up, and your whole plot's going to change, right? So that's why this is a static stability analysis. This only tells us how our plane flies at just a frame in time. So just keep that in mind, right? This doesn't have to be perfect, but I would recommend getting it perfect to prove that you have a statically stable plane. Okay. And here you can also see our CLCD for our whole plane, right? Versus alpha. Now, something really, really, really important to note, okay, is what you're seeing here is the alpha for your whole plane. So the direction your fuselage is facing. So if I went into my plane and I set my main wing angle to something crazy like 5 degrees, okay? Right now it's on 1.5 degrees, but if it were something like 5 degrees, and I was looking at my trim alpha, and I'm like, okay, we're trimmed at 2 degrees alpha, then my actual wing alpha, which is the thing that matters, is going to be at 7 degrees alpha. Since we have a 1.5 degree angle on our wing, we're at 3.5 degrees, right? 2 plus 1.5 is 3.5, okay? So when you're doing a PDR or a CDR, I always think it's a good idea to throw in, and sorry, if you don't know, PDR means preliminary design review. So when you're showing this off, CDR means critical design review. When you're doing that, okay, I like to put in our trim alpha for both our fuselage and our wing to make it clear that I know that the wing is flying at this degree. Because if I make our wing angle of incidence be 5 degrees and I go to my PDR and say, hey, we're trimmed out at 3 degrees, if I were in that audience, I'd raise my hand and I'd be like, so your plane, your wing is at 8 degrees, right? So if you pitch up by 5 degrees, you're about to stall. Okay? So keep that in mind. So I think I did a pretty good job explaining this. Really quick, I'm going to show you guys how to do not elevator, I'll do aileron deflections in this case. I don't have an elevator defined. You'd really want to use this for longitudinal static stability. You'd want to do your elevator deflections, again, to see that about a degree of elevator deflection is equal to a degree of pitch change. Okay, that was from the Aero and S&C lecture. Make sure you watch that if you haven't. So we're going to go ahead and go into our plane name and define our wing, just so I can show you guys how to do this, okay? It's a little bit strange. So define your main wing, okay? Now add a point after section 1, okay? This will be kind of a midpoint. And let's go ahead and change this to about, let's do 50 inches. No, let's do 40 inches, okay? And I'm going to go ahead and change this to our negative 15, okay? You'll notice it blends it together. This is not how a aileron normally deflects, right? Obviously, unless you have some kind of crazy morphing airfoil. So what we're going to go ahead and do is we're going to go ahead and insert before section 2 and have yet another point at 40. Now what this does is it creates a discontinuity instead of a flush point, right? From 0 to 40 we have a 6415, and then again from 40 to 60 we're looking at that negative 15 degree, okay? But now it is it's blended into the wingtip, okay? So now I'm going to define at the wingtip, I'm going to do insert before section 4, and at about, let's do 2 inches from the wingtips, let's do 58 here. I'm going to add another point, okay? So now our tilted up, if you can kind of see that, let me see if removing no, that does not help at all. Now you can see our tilted up section kind of blends in to a point farther down the wingtip, but it's straight now along here. So now I'm going to do another discontinuity, so insert before section 5 again, and make this 58. So I'm saying from 40 to 58, we have the NACA negative 15, okay, hit enter there. And then from 58 to 60, we're back to the normal NACA, 6415. So that creates this very nice looking discontinuity of how an elevator, or excuse me, an aileron would actually deflect in real life, okay? So I hope you can kind of see that. Maybe it's hard to see on your screen. Right, but look at that. Looks pretty nice, right? So I'm essentially putting 2 points on top of each other. See if I can make this bigger so you guys can see it. So from 0 to 40, we have our 6415, and then another 40 point to mark that discontinuity. 40 to 58, we have the deflected at negative 15 degrees. And then from 58 to 60, we have 6415 again. Okay, and this does it for both sides. So I don't believe there's a way. Oh, here we go. I thought symmetric was spelled with 2 M's. Am I wrong about that? Am I wrong about that? Yeah, symmetrics. I think they misspelled symmetric. Maybe it's like a British way of doing it or something. Again, if you ever want to do something with your life, remake XFLR. Sure, there's a market out there. So you could use this to define the left side to have that positive 15. Okay, so we're gonna do that, right? Because this is how ailerons work. If you're rolling the plane, you don't want this to be symmetric. That would just give you that'd be a flap basically, to give you pitch, right? So there you go, right? So this is kind of cool. I've never done this before actually, but now you can see our aileron deflection. So you would want to do this with the elevator in a similar fashion. And then so we're going to define that, and just for fun, let's try and analyze this. Theoretically, our pitch should be the same, right? Because in terms of the longitudinal direction, these are going to cancel each other out, because one's up and one's down in the same x position, right? You can kind of see that it's symmetric longitudinally. But let's go ahead and see. Let's see if that's true. Not really. It did actually shift it, right? But still, right? I mean, our trim alpha is pretty good. That's not bad. So there you have it, right? That's how you do control surface deflections. So I would recommend, if you have flaps on your plane, do that for every flap degree. Make sure that you still have a reasonable trim alpha for all your flap deflections. Ailerons don't matter so much unless you're going to do a beta, which is a side slip analysis, which you can do that by defining a type 1 and changing your beta. Oh, sorry, type 5 in a beta range. Set your alpha to whatever you want, and then sweep beta sequentially. Okay. So if you're looking at roll and yaw stability, do that. Yeah, you'd want to do your flaps and you want to do your elevator for longitudinal. Okay. All right. Now, real quick, we're going to look at span-wise distribution. So this is our wing here, wingtip to wingtip. And we're going to change this to, let's do our local lift coefficient. So this is with our ailerons. So you can see on our, well, this would be our right-hand side, right, if we're looking at the front of it. So this is technically our right-hand side, even though it's the left, because we're looking at it opposite, straight on. You can see our lift here is much higher, and then it's actually significantly lower on the left-hand side, right? So this is why our plane would roll in real life, is because we have so much more lift on the right-hand side of the plane. That's how ailerons work, right? They change that camber angle, they give you more lift. If we were to look at our first plane we defined, we'd have a symmetric lift distribution, because we don't have those ailerons chosen. But you can see, right, this is the one for our tail here, and this is the one for our main wing. You can see how those wingtip vertices are killing our lift. You can really see that. So it's very interesting. So that's that. Okay, so now I'm going to show you what is our actual Dodo XFLR analysis for that dynamic, because we have the masses already defined. I'm not going to go through and make a bunch of new masses. I'm just going to show what we did here, right? To prove that I don't want to do that, right? This is how many masses we have for dodos, okay? You can see our tilt rotors out front here have their own masses. We have the tilt rotor in the back, all the servos. We have things like the mass of our right wing, our aileron, our flap, all that sort of stuff, okay? And this is all pulled from our mass and balance sheet. I want to show you though, right? So we did our flap analysis for Dodo as well, right? So you can see our flaps are deflected there. And if we go to our plots here, right? So we have our 15-degree flap, we have our 5-degree flap, which has no analysis done for it right now. But you can see how that kind of changes your angle. So I'm going to actually close out a bunch of these. All right. So this is kind of how we found how our flaps behaved, right? Anyway, so let's go ahead and do a analysis. So I'm going to duplicate this plane so we have a fresh start. Let's go. I'll do this for video. Okay. So let's turn off our masses here. What I'm going to do is I'm going to go to analysis, and you don't have to follow along because you probably don't have this file. If you do, sure. But this is for if you're ever doing this on your own, you can follow along to this video and do it as I do it. So go to analysis, go to define a stability analysis, right? Now here we're going to mix 3D panels VLM2, viscous analysis, same everything, keep the mass inertia that you defined. Control parameters, this is for if you want your elevators to deflect and such. I don't have much experience with that, so I won't be going over that. And you can change your beta value for your flight attitude and everything. We're going to keep that as what it is, okay? And then save it, all right? Now you're going to get this guy pop up. This is for kind of defining your modes, which I'll get into, right? It's a pretty complicated subject, so I'm not going to go crazy on it. Here, in our case, we're not going to sequence a control parameter. We're going to keep that at 0. So all of our deflections are 0, and we're going to analyze it. Okay. So now's the cool stuff. All right. If you guys know anything about root locus plots, okay, XFLR put a great document out there for root locus, stability in general. If I can pull that up, where is that guy? Here we go. Okay. So this is their document for that. Okay, it's called Stability Analysis with XFLR 5. All right, it's a great source if you want to go through doing all this. Talks about VTails, how to do that. Talks about all the stuff I've talked about, CM alpha, CL alpha plots, right? Hopefully it agrees with everything I said. Talks about static stability, CG neutral point, all that stuff. And then it talks about our dynamic stability, okay? So this is a dynamically stable plane. Something that as it oscillates, it returns to its kind of trim condition. A dynamically unstable plane is going to go away from that trim condition. I said this in one of the previous lectures. The right flyer was statically unstable. But they were able to control it through themselves being the controllers. And they had essentially was a dynamically unstable plane that they could damp out themselves because these oscillations were slow enough. Okay. This talks a lot about eigenvalues and eigenvectors. If you don't know much about that, I'd recommend doing some research. It's a relatively complicated subject. But essentially there are a bunch of modes. Now these modes describe essentially oscillations and how those interact with the plane. So let's go ahead and look at that. What we have here is two different modes, two different longitudinal modes. Now, this is mode 1, this is mode 2, this is mode 3, and this is mode 4. Now, modes 1 and 2 describe our short period mode, which is how our plane responds to small perturbations in alpha. And then we have our phugoid mode here. Okay. Now, the closer that you are to the imaginary axis, the less damped out your oscillation is. So being very far from your real axis, your short period mode damps out very quickly. Being very close to the real axis, the phugoid mode does not damp out very quickly. You can see it is very slightly negative. If it were on the real axis, it would be neutrally stable, so it would never damp out. If it were on the positive side, if it were on the imaginary axis is what I mean, it would be neutrally stable. If it were on the positive side, it would be neutral. It would be unstable, completely unstable, and it would actually explode. It would not damp out. It would continue to be excited. So anyhow, right? This is our longitudinal root locus plot. Okay. So if we go to this guy here, okay, you can see that. I suppose I didn't really have it selected. And then we can go to, can I undock this? I can. I want to undock this. We can go to our lateral as well. Lateral has 3 separate modes. Okay, we have a roll damping mode out here. We have our Dutch roll mode for modes 2 and 3, and then our spiral mode. Our roll damping mode is super damped out. Our Dutch mode is not very damped out, and then our spiral mode is unstable, which is okay. Spiral modes are usually unstable. Okay, and I'll get into that. The closer you are to the real axis here, so this is on the real axis, describes kind of your frequency and how many oscillations it has, right? It describes kind of that transient motion. So on the real axis here, we have no oscillations, right? We go straight to our trim value. Okay, off the real axis we have oscillations, right? And these are pretty far, so we have a lot of oscillations off the real axis. So I'm going to go ahead and show that now. So if we look at our time history plots, we're going to first look at modal response. That's a good way to look at them. And we're going to start with longitudinal. Now mode 1 and mode 2, I said we're a short period mode. We're going to keep this at 10, we'll go to 5 seconds. It's a very short period mode. And then we're going to go ahead and add. Okay. So you can see, right, that damps out almost immediately, right? Within 1.5 seconds. It's about 2 seconds. It's hit its steady state value. Okay, it's damped out. So if we look at our longitudinal modes again, right, they're very far from that imaginary axis. They damp out very quickly. And you'll see because they're not on the real axis, right, they overshoot. Okay, they oscillate. So then, let's go ahead and look at our mode 2, which is the exact same, right? Modes 1 and mode 2 are for that short period. Then mode 3 here is our fugoid. Now your fugoid, right? Whoa, what is that? Well, let's delete everything here and let's go to 100 seconds, right? I said that is barely off of that imaginary axis. So if you hit R on the plot here, you can see, right? It is damped. It is stable. It gets smaller and smaller, but it is very, very slightly stable, and it oscillates a lot, right? So we go back here, you can see it's basically on that imaginary axis, okay? And it has quite a long period too. So anyway, right? You want to look at this. You want to make sure that you have a stable plane dynamically, and you want to see your period. Okay, this is a pretty short period. This is like, I don't know, 8 seconds or so from point to point. So you know, a longer period would probably be better, but this works for us. So now let's go ahead and look at our lateral modes. Okay, so mode 1 I said was that roll damping. This one has no oscillations. So let's go to 5 seconds again and let's add it. Right, look at that. Go straight there. Mode 2 and mode 3 are our roll damping. So we're going to delete this. We're going to, sorry, not roll damping. It is our Dutch mode, Dutch roll mode. Let's go to 20 seconds here. And let's turn on mode 2. Right. So you can see this one damps out within 10 seconds. But there are a few oscillations. It damps out relatively quickly. So if we look at our lateral mode, right, that's got some distance from the imaginary axis. And then mode 3 is the exact same as mode 2, so let's delete that. Mode 4 is our spiral mode, which I said was unstable. So if we add that, right, just zooms off, okay? And you can see that here. And again, no oscillations, right, because it's on that real axis. So what you can do, which I like doing to show people, is you can look at your modes, right? Mode 1 and mode 2 are that short period that describes a change in alpha. So if we up our speed and our amplitude, just so you can see it a lot, hit animate, you can see that alpha changing, okay? Let's go to the side view for the longitudinal guys. And look at this, right? Boom, boom, right? Very quick response, okay, to small perturbations. Now, fugoid mode describes, it does not describe a change in alpha. You'll notice we are not changing alpha here. It does describe essentially pitching up, losing speed, losing lift, pitching down, right? Relative to your airflow, so you're not changing your alpha, you're just changing your flight path angle. And then you're gaining airspeed, gaining lift, going back up, losing lift, and then getting it, right? So your longitudinal flight is dictated by a combination of these two modes, okay? Now for lateral, let's look at 1. This was our roll damping, so let's look at it from the front. Boom. Really simple. As your wing comes down, there's a high pressure air under it that resists it coming down. Now, that was just a rolling moment. Our Dutch roll, our 2 and 3, are a combination. They're the coupling of roll and yaw. Okay. The bigger your vertical stabilizer, the less Dutch roll you're going to see. And for this plane, we had a pretty good big vertical stabilizer, and it damps out pretty well. Okay. This is a cool one, though. You kind of see it. Right. Now, 4, this one's funny. Let's go to the top here. 4 is our spiral mode. As I said, that's unstable. So it's on the positive side of the imaginary axis. So it will just keep on going. It will just fly off the screen, right? This is so very slightly unstable. Again, I've upped the amplitude and the speed. That as a pilot, right, you just you damp this out without even thinking about it. You control this yourself, okay? Just very low gain inputs. We'll do that. So that was a description of our dynamic stability. So after you've done your static stability, you need to show that your plane is statically stable. And then you should show that it is also dynamically stable, okay, by doing your masses. If you don't have masses at the time that you're doing this, static is fine until we get masses. But, you know, use your resources to weigh your wing, right, whether that's through your CAD or actual weighing. So that, you know, if you're doing a special wing or something, and you're looking at, specifically for our modular plane this year, that's why I'm saying it, and you're looking at how that's going to interact with the actual plane, and you don't have the plane masses yet, wait until we get the plane masses, but make sure you have the masses for your wing ready to go to throw into there, okay? So that should be it for XFLR, and that should be it for my series. If you guys want me to make any other videos, let me know. If something was confusing, reach out to me, James Wadhwani, okay? Um, otherwise, this should be good. So yeah, thank you for tuning in. I don't ever use that plot. Anyway, thank you for tuning in, and I will see you guys later. Bye bye.